Hi everyone, welcome to the 8th lesson for topic 4.4 Newton's laws of motion. This is also the last lesson under this topic. Alright, so yeah, let's look at the learning outcome. So same thing, we are going to solve some simple problems which can be modeled as the motion of particle moving vertically or is in a connected particles. Okay, so the system that we are going to look at is the object in the moving leaves today. Okay, so all the questions that we'll be doing is about the moving leaves only. Alright, so let's start with a simple introduction before we move on to the four examples that we have. Alright, objects in moving leaves. So there will be two main theory that we'll be using for today's lesson. The first one is Newton's second law of motion, which we talk about F equals to ma. So that's basically the main formula that we'll be using today. Then after that, we'll be doing some Newton's third law of motion also. It's just using the concept. So like for every force, there will be an equal and opposite force. Okay, so you do not need any super formula or resolving forces in this case. Yeah, so there's no resolving because it's basically one direction, right? When we talk about moving leaf, you can only move vertically or downwards or upwards. It cannot be any other direction, right? So that's the idea. Okay, so when a person travels in the lift, as you can see in a picture here, so you can see that the only connection between this person and the lift is actually by the floor of the lift, right? So that's why the floor of the lift acts as a connection between the person and the lift. So when you try to look at this, right, you'll realize that it's a bit different with the situation that we have previously because no matter you talk about pulley or we talk about, let's say a simple idea, when you try to use a string to actually pull something, right, the force is actually acted directly on this object by using the connection of the string. But when we try to look at the leaf, right, even though the person moved, but it's actually not directly pulled by the string. Am I right? It's actually because of the string is pulling the leaf and then the person is in the leaf. So you have this connection between the person and the leaf as well. So now we'll be looking at these three different situations, which the first one is what happened to the whole system, to the person and to the leaf when the leaf is stationary or moving with constant velocity. So which basically the first one we talk about the force in equilibrium, right? Because there's no acceleration involved. Then after that, we'll be looking at the second and the third one, which we have acceleration. One is accelerating upwards and the other one is accelerating downwards. Okay, so let's try to solve the first one first. So let the m, the small m, be the mass of the person and the big M be the mass of the leaf. So what happens if the leaf is stationary or moving with constant velocity? Okay, so now let's try to look at it in as if it's in a system first. So that's why we know that all the internal force is going to eliminate each other. It's the same thing like the previously we talked about if let's say it's a pulley, right? So that's why for the part where there's tension, so it's going to eliminate each other. So in this case, right, the internal force that you have is basically the force between the floor and also the person here. So that's why the normal reaction, we are not going to look at it when we try to look at it in a system. Okay. So when we try to look at it as a system, then definitely for the external force, the one that we have is like the tension of the string here, right? Then after that, the second one that we have is the is the weight of this leaf itself. So that's why if the mass is the big M, so which means we have the weight, which is mg, right? Then after that, the for the whole system, the weight of the person, of course, it contributes to the weight for the whole system as well. So that's why we'll be having the weight of the person as well, which is the small mg. Okay, so we know that when forces in equilibrium, there's no A involved. So the A is zero. So which means that the forces moving upwards and the forces moving downwards is basically the same. So that's why the net force is zero, right? So that's why by looking at this case, we know that the tension should be equal to the mass of the leaf plus the weight of the leaf plus the weight of the person here. Okay? Yeah, I think that's pretty simple, right? So which means if let's say it's stationary, then yeah, basically the tension is just the same. So that's why there's no A. Okay, so second one, what is the force that actually acts on this person? Or what's the force that actually acting outwards of this person? So we know that from this person, then definitely is going to be the weight of this person, right? So which is mg. So this person is get in touch with the surface of the floor. So that's why there will be a normal reaction moving upwards. Okay, so since this is in stationary as well, so that's why we know that the normal reaction is just basically equal to the weight of this person. Okay, so this is something that is, I mean, we normally use these two more common, but then we can try to talk about this as well. So when you try to look at the forces on the lift, so which mean that it will be a tension from the strain, okay? Then the weight for the lift itself. Then after that, because of the person is get in touch to the floor of the lift, right? So that's why there will be normal reaction acting from the floor to the person, and the person will actually contribute the normal reaction as well from the person to the ground. Am I right? So which is R. So in this case, you can actually think of it as if the normal reaction is the same thing like the weight, because in this case, you can see the R is mg. But later when we try to look at accelerating, then you will see that the normal reaction doesn't normally equals to mg, because for this person, right, it's not in equilibrium anymore. But in this case, yes, you can try to think of the weight that is the weight that actually acts on this floor of the lift, but then we call it as the normal reaction because of that's the force that acts on this surface by the person here, and is actually equal and in opposite direction of the normal reaction acts from the surface to the person. Okay, so that's the idea. So that's why by using this, then you can see that you get it the same thing as this one, so which is like T is equal to mg plus R, which in this case our R is basically equal to the mg, so T is equal to mg plus mg. Okay, so that's the part if let's say the lift is in stationary. Okay, so now let's try to look at what happens if let's say the lift is accelerating upwards. So we have this lift accelerating upwards, so we try to let our motion or our A going upwards be positive. Okay, so similarly, the force that will act on this system is the tension, and then after that the weight of this person and the weight of this lift. Okay, so now because the lift is accelerating upwards, right? So which means that the net force exists as if the tension here should be larger than the total weight here, so that the lift can be accelerating upwards. So the idea of it is the net force will be equal to the tension minus of the weight of the lift minus of the weight of the person here, and equal to the net force, equal to the MA. So what's the MA here? So it's the total mass. So what's the total mass involved? So it will be the big M and also the small m, right? And then multiply with A. So that's the acceleration that we have. So this is the formula of net force equals to MA. Okay, so now let's try to rearrange it a little bit by using our T in front. So because later I want to compare with what we have here. So T will be equal to, I think we can take out our G as well. So M plus mg and then plus M plus MA. Okay, so from this picture, right, you can definitely see that if let's say I were to factorize this also, then I will get M plus mg as well, right? So you can see compared to our first picture, when the lift is accelerating upwards, the tension is actually larger than the one which is in equilibrium, which makes sense, right? Because of the tension needs to be like higher so that the lift can accelerating upwards. If not, then it will be just nice for it to, I mean, stay stationary or move in a constant velocity, which didn't provide any net force. So you can see that the extra forces that you have is actually under this part. So where this is like the one that we have that's in normal reaction, then this is like the in normal equilibrium. So what we have here is like the extra forces that create the net force to this lift. Okay, so now same thing, let's try to look at this person. So similarly, the force that acts on this person, so we have this weight, then we have the normal reaction. So in this case, since the lift is accelerating upwards, right? So which means the same thing, the normal reaction should be greater to the weight of this person, right, then is equal to MA. Okay, so as what you can see here, if let's say we try to rearrange it, then we will get R equal to mg plus MA. So that's why when you try to compare to the equilibrium one, you'll realize that there's an extra force here. So that causes the normal reaction, in this case, become bigger. Okay, so you can try to imagine, right, when you are in a lift and the lift is actually accelerating with a high A, then you experience the idea where you feel like driven to the ground. And then, okay, let me try to use another example. So if let's say you are you know what is that called in the playground? Okay, I don't know what is that called, but that's the idea. So you know that that's like a game that you need to sit on the chair, and then after that the thing will actually move upwards, then you're accelerating down, so stuff like that, right? So like, okay, so imagine you are sitting on the seat here. So normally when it's going up, right, what do you realize is that you will feel like you are driven harder to your seat, and then you will feel like there's a force that coming out from the seat to yourself. You feel like you are basically heavier than normal. You get what I mean, right? So the force that you actually feel is basically caused by this normal reaction. So you see, the normal reaction that you feel, right, is more than the normal weight that you have. So that's why you feel like there's like a lot of forces that actually pulling you down to the ground. So that's the idea when you are on something that's accelerating upwards. Okay, so now let's try to look at the lift part. So this is the part that you can't feel out because this is the force that actually experienced by the lift. So the same thing here, we have big M, then G, then R, and also the tension. Okay, so similarly, the tension, the force moving upwards is going to be more than the force moving downwards. So T minus of mg minus of R will be equal to our mass here only, right? So MA. Okay, so what do you realize here, that you see, right, the R here is based on this situation. So you can see the R here is not only the weight only. Okay, so make sure that if when you are using this equation, do not always assume that the R here is the weight of this person, because it's supposed to be the normal reaction, and the normal reaction depends on whether the leaf accelerating or not. Alright, so now when we try to rearrange it, then we will get T is equal to, let us try to rearrange it and substitute everything that we have maybe. So mg and then plus R, right? So our R is mg plus MA and then plus MA. Okay, so it's okay, I'm not going to rearrange it, but basically the idea is you will get you will get more force, you will need more tension compared to the first one in equilibrium as well. Okay, so that's the idea. Okay, so now let's try to look at the last part, which what happened for the lift is accelerating downwards. So same thing, let me try to label all the force first. So we have mg for the person, mg from the lift. Then after that, we have this tension. Okay, so when we try to look at this, then what do we see is that the lift is accelerating downwards, right? So we try to denote that going down as positive direction. Okay, so if that's the case, so meaning that the weight here should be greater than the tension here, so it creates a certain net force. So that's why what we have here is the mg plus mg minus of T, then we will get the total mass multiply the acceleration, right? So F equals to ma. So now same thing, let's try to rearrange it and see what do we get. So T will be equal to, so you see when you try to move this, okay, so which means we try to move the negative T to the other side, move this in front. So what do you realize here is we try to do the factorization as well. So we get m plus mg, then minus of m plus ma. So that's why what you realize here is that this tension is basically lesser than the one in equilibrium, because you need to minus off the force here. So which is correct, right? So you imagine when you try to use a machine and you want to pull a box, let's say you want to pull it upwards, or you just try to put it on the ground from a higher floor, then you can see that the tension that you'll be using is basically different. So the idea is that you will require lesser force if let's say this lift is accelerating downwards. Okay, so that's why you can see the tension is actually minus of. Okay, so now what happened to this person? So same thing, we have the weight, then we have this normal reaction. Okay, so for this part, accelerating downwards, so mg minus r is equal to ma. Okay, so when we try to find the r, then what do you realize? So you will see that it's equal to mg minus ma. So you can see the normal reaction is actually lesser than normal, right? Because if let's say this is your weight, then you minus off ma. So which means the normal reaction that you feel is actually lesser than your weight. Okay, so you can imagine the same idea that we use here. So when you try to play this in a playground, right, then you will realize when you are in the top part, and what happened is when you are trying to accelerating downwards, right, what do you feel from the seat? You will normally feel like this is why you need the safety belt, right? Because you actually feel like you are going to fly out from the seat. So you are going to like shoot out from the seat. So you feel like lighter than your normal weight. Okay, so that's the idea of why do you feel so? Because of the normal reaction that you are feeling now. It's normally lesser than your weight. Okay, so that's the idea. I hope that that help you to like imagine or visualize a bit. Okay, then after that, the last one, same thing. So mg big M, then after that, the normal reaction and also the tension. So you can actually imagine it's roughly the same with our first one here. So that's why I say that we normally didn't use this so much when we try to compare to like the first two lah, because for this one it's actually same complicated like this one. So normally we'll try to solve the R here, then we'll see how are we going to carry on. Okay, so yeah, that's the idea. And it's the same thing like when we talk about the tension and the acceleration. So which means if let's say the same thing like in pulley system, right? If the question doesn't want us to do not need us to find out what's the tension is, then normally we can use the complete system because you realize there's no normal reaction involved. So if you are using this tool, then which means that you should be able to get this first, then you are going to use this to your second equation. Okay, that's the same idea with like what we how we solve a pulley system. Okay, so same thing here. So which means the mg plus the normal reaction, then minus of the t is equal to big ma. Okay, so let's substitute some of the thing that we have. So we can see mg minus mg, sorry, this is plus minus of ma minus t equal to ma. So when we try to rearrange it a bit, so the t will be equal to m plus mg, okay, minus of then same thing m plus ma. Okay, all right, so that's the idea. So you can see that you're actually getting the same thing because of, you know, when we try to use this, because what we are doing here is actually simultaneous already. I hope that you can understand. I mean, maybe you have a doubt that why do we need to do the complete one if let's say we can get it here, because what we are doing here is actually we are doing our simultaneous equation already so that you get your last, so that in this part you can actually see that actually this is just the same thing when we try to do combined system. It's just the same thing when we do the simultaneous equation from the two equation here. Okay, so I hope that you can see like the relationship, because when we try to solve simultaneous, then what happened is that the r here is going to eliminate each other. So that's why what we left here is basically what we find out from the combined system. Okay, so I hope that you can get the idea of the interaction here, and we're going to look at four examples here. Alright, example 1 and 2 is very simple. If you want to try out by yourself, feel free to do so. Okay, so 1, a passenger of mass 60 kg is in a lift of mass 500 kg. The lift is operated by a cable. Calculate the force R exerted from the floor of the lift on the passenger. Okay, so we talk about the system of the passenger only, so which means it's like a separate equation. So now since that the question didn't tell us that the lift is accelerating, so we assume that the passenger just go in, then the lift doesn't move yet. Okay, so let's try to, you can have an idea of it. So the person on the lift of the on the floor of the lift. Then after that, it will be the weight of this person. Then there will be normal reaction from the surface of the lift, then onwards the people, right? So that's why we have the normal reaction is just equal to the weight of the person, which is equal to 600 multiply 10, which is 600 Newton. Okay, so now for B, the tension T in the cable when the lift is accelerating 2 meter per second square upwards. So moving up is positive direction. So now we talk about the tension in the cable, so that's why we can try to look at it as a combined system. Okay, so we doesn't need to solve simultaneous equation since we do not need the normal reaction as well. So in this case, we have this tension moving upwards. Okay, then after that, we have this person inside the lift, right? So that's the weight contributed by the lift, and that's the weight contributed by the person. Okay, so we can write down our equation first. So accelerating upwards, so which means tension is greater, minus of mg minus of mg, and is equal to ma. And don't forget your m should be the total one. So let's try to just write it. Okay, so tension will be minus the mg here. We have 5,000. Okay, the weight of the lift, the weight for the person equal to the mass 500 plus 60, then A is 2. Okay, so just solve this simple thing. So we have it's going to give us 1120 and then plus 5,000 plus 600. So the tension here is 6,720 Newton. Okay, so that's it for number 1. So let's look at number 2. Okay, number 2, a man of mass 80 kg and a woman of mass 70 kg are traveling in a lift of mass 500 kg. Okay, so let's try to draw it out. So we have the lift. So inside the lift, we have this man. Okay, so the mass is 80 kg, so it's 800 for the weight. Okay, then we have this woman. Yeah, it's okay lah. Then after that, the weight here is 700. Okay, so it's traveling in a lift of mass 500 kg. So the weight will be 5,000. Okay, for the lift. So the tension in a cable pulling the lift upwards is 6,890 Newton. So that's tension. Okay, so find out the acceleration of the lift and the reaction forces between the lift floor and each of the passenger. So there are 3 things that we need to find basically. The first one is what's the acceleration of the lift. Basically, it's the acceleration of the 2 person as well. Then after that, the last one is find out the normal reaction on the passenger of the man and the passenger of the women here. Okay, so now let's try to solve the acceleration first, because by having all this, we can actually look at it as a combined system already. Then we can straight away solve the acceleration. So the tension minus of all the weight that acting downwards. So this one is actually pulling the lift upwards as well. Yeah, so that's why our A is moving in a going up is a positive direction for us. So minus of the weight of the lift minus of the weight of the woman, then equal to, okay, the mass, total mass, and then A. Okay, then basically we got everything here. So from here we can get 650A equal to 390. So that will actually give us acceleration is equal to 0.6 meter per second square. Okay, so after we found this, then now we can solve for the reaction force. So if you need it, then you can always try to draw it again lah. So if let's say this is like the man, okay, so you always have the floor here, right? So that's why the weight going down, then we want to find the normal reaction that's going up, right? Then the same thing here, we have this woman. Okay, so the weight here is 700, then the normal reaction going up. Okay, so you can see that because of they are having a different weight, right? So that's why their normal reaction will be different as well. Yeah, so even in an equilibrium, then you definitely see that, because if let's say it's in a liquid equilibrium, then your normal reaction will just equal to your weight. So that's why now plus the net force, then it's going to give you a different answer as well because of your mass is already different. So when you do MA, it's going to give you different and MG is different as well. So that's why let's try to solve for the man first. Okay, so for the man, the net force that we have is the normal reaction minus of the weight. It will be equal to the mass of the man, then multiply the acceleration, right? F equals to ma. So the R here will be equal to 48 and then plus 800. Okay, so which is going to give us 848 Newton. So now same thing for the woman. So the normal reaction is bigger as well because it's accelerating upwards. So R minus of the weight equal to the mass multiply the acceleration. So from here, then we can get R is equal to 42 plus 700. So which is 742 Newton. Okay, so that's basically the idea of these two questions. So yeah, it is very straightforward. Okay, so now let's look at number 3. Okay, number 3, a man of mass 80 kg stands in a lift. The mass of the lift is 400 kg. The lift starts to travel downwards with an acceleration of 8 meters per second square. Okay, so now the lift is traveling downwards. Alright, so with an acceleration of 8 meters per second square. So we have, let's try to draw the lift. Okay, so this man of 80 kg, 800 for the mass. Okay, so the mass of the weight is 400, so that's why it's 4,000. Okay, so yeah, the tension of the lift cable is KR, which R is the contact force between the man and the lift floor. Okay, so this will be like a simultaneous equation that we'll be solving because the T now is related to our normal reaction. Okay, so that's why we might need to find out our R first so that we can solve our K. Alright, because we know that when we try to look at them in a separate system, right, then we can obviously solve what is our normal reaction first from the equation focused in the person itself. Okay, so that's why by looking at the force of this person, so we know that we have 800, then the normal reaction, which is the contact force, right? Okay, then after that, this thing is moving downwards 8. So that's why F equals to ma, so 800 multiply the contact force, which is the R. So in this case, the contact force is only the normal reaction because there's no friction involved. Okay, then after that, 80, then the A is 8. Alright, so from here, then we can get our R is basically equal to 800 minus of 640, which gives us 160 Newton. So after we get this, then now we can look at the combined system and we try to solve the tension. Okay, so similarly, so moving downwards, so is 4,000 plus 800 minus of KR. It will be equal to our total mass 400, 80, and then acceleration. Okay, so let's substitute everything. So 4800 minus of K is what we want to find, right? R, we already got it, equal to 480, acceleration is 8. Okay, so 160K will be equal to, so when you try to solve this move here, then this one move in front, then you'll get 69960. So the K, after we solve it, then we can get 6. Okay, so I think this is, yeah, very simple as well. So now let's try to look at the other question, which might be slightly harder because we are going to look at the part where the pulley and the lift together. All right, number 4. So you can see that I put a line here. So it's just I want to split it into like 2 columns so we can write in 2 columns because I doesn't want to use an extra page for this single question. Okay, so two masses A of 2 kg and B of 3 kg are connected by a light inextensible string that passes over a small smooth fixed pulley. Okay, so this is like the vertical pulley system. So initially the masses are held stationary and then released. Okay, so you should be pretty familiar with this type of question already. So let us try to just draw it. So this is part A. Okay, so we have the pulley, then we have the mass of the 2 kg, which is the A here. So 2 kg is 20 as the weight. Then the other side we have B. Okay, so this is 30 as the weight. Okay, so it's connected by this pulley system, so that's why we have the tension and the tension. Okay, then after that, the masses are held stationary and then released, right? So the question wants us to find out the acceleration. So you can see that the B here is having a larger force. So that's why we can actually see that the pulley or the particle is going to move in this direction. Okay, so since the question only wants us to find the acceleration, we can always use a combined system to help us to solve this. Or if you want to use simultaneous also can. I think this is pretty simple as well. It's just like 30 minus of the t, and then after that t minus of the 20. So it's just the same thing lah. Okay, so find the acceleration. So we can straight away look at combined system. So we have 30 minus of 20 for the net force equal to the total mass, which is 3 plus 2. Acceleration is what we want to find. So 5a will be equal to 10, which a is basically 2 meter per second square. Okay, so this is the idea. So like the mass of B is actually moving downwards for 2 meter per second, A is moving upwards. Okay, so now the pulley is fixed to the wall of a lift. So the lift is initially stationary. The lift has mass of 400 kg and a man of mass 75 kg. So let me try to draw it out first. So this is for part B. Okay, so we have this lift now. So this pulley is actually put on the wall. So let's try to just put it here. Okay, then we have this man. Okay, so the lift has a mass of 400 kg. So it's 4,000. So the mass of this person is say 75. So 750. And don't forget, this pulley is going to give you the mass as well. So you can see that yeah, they try to give you that this pulley is actually a small one. So that's why you can imagine like the string and also the pulley didn't contribute any weight here, okay, because it's a very light one. So but we need to take into the consideration of the particle of A and B. So that's why it's like 2 kg and 3 kg, so total 5 kg, so the total mass is 50 from the pulley. Okay, so this is what we have. Then after that, there's nothing else in the lift, and the lift starts to move upwards from rest by a tension of 4,992. Okay, so now what do we need to do is to find out the acceleration of the lift. So I think we can try to use net force here as well. So 4,992. Let me try to write a little bit over the other side. So yeah, 4,992 minus of 50 minus 4,000 minus 750. Okay, so yeah, you can read it out, right? The question gives you that is moving, starts to move upwards. So that's why our net force is actually the tension will be bigger than the other. Okay, so that's why it's 4,992 minus of the other. Then equal to the total mass that we have, 5 kg from the pulley, 400 from the lift, and then 75 from the person. Then the acceleration is what we want to find. Okay, so from here then we can get 5, so 480A, that equal to 192. So the acceleration is equal to 0.4 meter per second square. Okay, so this is acceleration when it's moving upwards. Okay, so now C, find the acceleration of each A and B as viewed by a person standing stationary outside of the lift. Okay, so you can see that the idea is that the pulley is fixed to the wall, then the lift is stationary. Then after that, when everything is ready in the lift, right, then the lift starts to move upwards. So we can imagine that the part where the pulley starts to move, is basically the same part when the leaf starts to move upwards as well. So if let's say there's one person that's standing stationary outside the leaf, right, what it can see is that this pulley, okay, so definitely from the first stage, you can see that this thing is moving like 0.4, I'm sorry, it's 2 meter per second square from the pulley system. So this is 2 meter per second square. So for this part, it's actually moving upwards, right? Moving upwards by 2 meter per second square. So now when this person try to look at it from the leaf, right, meaning that he will actually look at the motion of the leaf as well. So I'm going to use the other color. So what happened here is that when the leaf is moving, we will have an acceleration of 0.4, and that's like moving up. Okay, so 0.4. So that's why when we try to put them together, right, then what do you realize here is that these two acceleration is actually move in the same direction. So this is for particle A, this is particle B. So let's try to look at particle A first. So particle A, the pulley is moving upwards and the leaf is actually moving upwards as well. So that's why for their relative motion here is going to be like 2 plus them together, because you can see the motion of the leaf is actually helping the leaf to moving up already. So the pulley is eventually moving upwards, and now the particle is moving upwards as well. So that's why the overall acceleration for A, it will just be equal to the 2 and then plus 0.4, and it's going to give us, sorry, let me try to write A. So this is for particle A. Okay, so for particle A, so both direction is moving upwards, right? So that's why it's going to be acceleration equal to 2 plus 0.4, which is 2.4 meter per second square. So this question, you might be a little bit careful that you need to write down. So if let's say there's no, I mean, the question didn't give us like you want to move up or move down. So in this term, it's like 2.4 meter per second moving upwards. Okay, then which means that in this part we try to take like going up as positive, this part we try to take going down as positive, so moving upwards. So now for the B, what do you realize here is that the leaf is actually moving upwards, but this particle is actually moving downwards. So the relative will become minus because they are moving in a different direction, right? So that's why when the person try to look at the particle B from outside of the leaf, then he will actually see that this, I mean, although the leaf is actually moving upwards, but this B having a larger acceleration, so it's dropping down. I mean, it makes sense, right? You can try to imagine if, let's say, this pulley move inside the leaf, and we try to look at it from the outside, then you should be able to see that the particle is still moving down, but maybe it's not so accelerating like this one, because at the same time, the leaf is moving up. So that's why for B, the acceleration will be equal to 2 minus of 0.4. So for this part is 1.6, but remember to write down as if this is positive as well, because we are trying to look at moving downwards as positive. Okay, so if you were to write moving upwards, then it will be negative 1.6 then. Okay, so that's the idea. So yeah, just to tell you that if let's say this person standing outside stationary look at this leaf, right, it's going to be like this. If let's say this person is the one that inside the leaf looking at the pulley, right, then it will be just eventually like this here, because the person here is actually moving in the same acceleration as the leaf, as the pulley as well. So it cannot actually observe the total acceleration. I mean the relative acceleration happens here. So you'll just look at what it is happen for the pulley. Okay, so that's the idea for number 4. So spend some time to do your work. I think this part is very easy. Then you can start to do some revision or like some chapter review question for this chapter already. Alright, so that's it for today's lesson. Thank you. See you in next week.